Hey guys, this will be a relatively long video that we'll do today for talking about neural network activation functions and basically finishing off day three as soon as possible, right? So the first thing that we'll focus on is something very, very specific. We will talk about ReLU, right? And activation functions. So in a nutshell, let's start it off. Import torch, torch, and now x is equal to torch dot random. I'm using the random function to generate random things, basically random numbers, and then I'm going to just print x. Okay, so now it's given me this. Now what I'm going to do is I'm going to actually do a ReLU output for this. So I will explain to you why the ReLU output is usually sometimes broken, right? So print ReLU out. Okay. So now it's giving me 000. So if you can see over here, when it's 000, it's already causing a few issues, right? Um, let's say, for example, we have a tensor and let's actually calculate the gradient backwards. So here I created random, right? This is ReLU, rectified linear unit. Basically, any negative value goes to zero, any positive value remains the same. So if it is positive, let's just hope we get a positive value. Yeah. So now we got all three positive. So all the three positive values stay the same. But if it's a negative value, it goes away. So let's imagine we had torch dot tensor of, let's say, 1.0, or no, let's go negative 1.0, then 0.5, and then negative 2.0, right? Now we can say requires grad as true, right? Now what we can do is we can again say print ReLU output, we can do the same. We can also do, okay, something very, very simple. We can also go backward, okay? So instead of ReLU output, I'm just going to write y because it's simpler for me to write y. We'll just print y instead. We are going to do y dot backward, okay? Now I will calculate x dot grad, okay? So now let me comment out this top part. Oops, grad can be, oh, for only scalar values. Wait a minute, what did I do? Torch dot tensor print of x, okay. Um, okay, it's printed y dot backward, print x dot grad, y dot. Okay, so there's a bug in y dot backward. What is the bug in y dot backward? Um, um, um. Oh wait, uh, I think we're doing a ReLU, right? So grad can only be inserted for scalar outputs. Uh-huh. Hmm. Wait, actually, let's explain this error. Then one value. Okay, okay, okay. Got it. Okay. Yeah. So it's not on a this thing. It's on a scalar value. So you need to actually sum it and then do it. Scalar means it's like a single value. I can't do this if it's got multiple values. That's basically what it means. The loss must be a single number, and only on top of that we can calculate it. We can't calculate it over everything. Does that make sense? That's another small thing that now you learned through this. But as you can see over here, if you do calculate x dot grad, you see the grad value itself is zero, and this means that there is no change. There will be no change in the neurons before this. This creates a dead neuron problem. Okay. So because it creates a dead neuron problem, what happens is the neurons themselves can't change. Okay. And what do we do to prevent this? We can just use leaky ReLU instead of ReLU. right? So instead of this, you would say phi is equal to not sigmoid. You would say torch dot nn dot functional dot relu. Nope, not even relu dot leaky relu, right? So even for for small values, it would it would work. So have a look at this. So if you can see over here for -1, it does negative minus 0.01 and zero point 0.5 and negative 0.02. So the way leaky ReLU works is such that it doesn't make the gradient zero. For leaky ReLU, that allows a small non-zero gradient for negative inputs. So you can see it gives a really tiny inputs which scale towards zero, which go towards zero, right? And I think what we can do is we can just check the function. Um, oops, that page is gone. Okay, click on this. Yeah, leaky ReLU is equal to max of 0 plus negative slope star minimum. So I believe the default value of negative slope is 1 e to the power minus 2. So that is why we saw 0.01 multiplied by the negative value. That's basically what we are getting over here. Because x is -1, so we got that value, right? That's basically how leaky ReLU is carried. So maximum of 0 comma x. So if x is -1, then it's -1, and then star minimum of 0 comma x, right? So if it is greater than 0, so this is a very easy way to do leaky ReLU, a very elegant way. All right. So that's basically leaky ReLU, and that prevents the problem of having a completely zero gradient. So it's a bit better, right? Similarly, we have other functions as well. We have y is equal to torch dot sigmoid, sigmoid of x, right? So sigmoid, if I were to write, is Pytorch is basically a value between 0 and 1, okay? Squashes it between 0 and 1. So look, it always squashes it between 0 and 1. So this is the loss, and this is how the tensor appears, okay? And now we can do this in another way as well, right? We can sort of figure this out in another way. What we can do right now is we will introduce a few more functions other than ReLU, leaky ReLU, and sigmoid. We'll introduce tanh and softmax. Okay, so if it is tanh, what it does is the outputs are same as what we had before in ReLU. I mean, sorry, as in sigmoid, but it is a bit more centered around 0. So right now these are centered over here, right? So if I were to wait, if I were to comment this out, please remember this value of 0.28, 0.62, 0.11, 0.192310. This will now center around 0 a bit more. 0.42, 0.78, 0.7. And this tensor is also much closer to the 0 values, as you can see, negative 0.0426, so on and so forth, when compared to if it was this, right? You see these values, they are all like 0.28, 0.62, 0.11. And now if I were to do this, you can see it's negative 0.96. So it's slightly different. It's slightly different from your typical this thing. And you might ask me, why do we use tanh over regular old this thing? Well, we can actually Google it. Tanh versus sigmoid. Why? Right? And tanh is often preferred for hidden layers because it is zero centered, meaning its output ranges from -1 to +1, which helps with faster convergence during creation. Whereas sigmoid is due to 0 to 1. Yeah, sorry, my bad. I had forgotten. It's -1 to 1. Sigmoid just squashes it between 0 and 1. This is between -1 and 1. That's why tanh has that. So it's centered around zero. So the center of it is around zero. That's what I mean. Now even I understood. I had sort of like forgotten parts of this. And finally, I would like to introduce you guys to Softmax. So Softmax is basically a probability distribution. That's basically what it does. So, and it should softmax over a certain bunch of values, right? And softmax in itself is not used, but it is used to basically get the output probabilities. That is how it is usually used, right? You have the logits, then you have the probabilities, and you have the sum of probabilities. Okay. So the probabilities are what we get by doing softmaxing of the logits. Okay. And the logits will be any subsequent layer output. Okay. So for example, I'll give you an example. We don't necessarily need to, what do you call it? Wait, actually, what we can do is, what softmax? I should have commented the other one. Right. This will not work, obviously, because you're summing it. This sum will always become one. Uh, so wait. Negative one requires grad. Okay, one second. Tensor input dimension. Yeah. So yeah. So this is along dimension zero. That is the lowest dimension. That is just to do it. And usually almost always you can see these are basically zero. These are like e to the 0 8 0 minus 9. It's basically zero because the loss is one. That's why. So when you softmax anything, and if you print it, it just give you a probability. So if you add these three numbers together, you would get like very close to 1, or you will get exactly 1. 0.17 plus 76 is basically like 95 or 94. It's like 0.94 plus 0.6 0.06 is like 1. So this is like 1. It'll sum up to 1. So if we sum it, it's giving 1.00, which is perfect. Then if we find the gradient, we see it's like really really low in this case though. Okay. This is sort of meaningless, but this softmax basically is to do probabilities. So if you got logits are any tensor like this, you can compute the probability that this is -1 plus 0.5 plus, so it's -1. Wait, actually, I can just show you the softmax function. I think we did this before, but it's important that we do it again. Oh yeah, e to the power zi divided by summation of e to the power of zj. So it sums everything and then e to the power of that numeral divided by that. That's basically softmax. Okay. Now that we have done softmax, we're going to create one very simple neural network. This neural network will have a batch size of three input samples with four input features, right? And the parameters that we're going to make it learn are maybe um, four. Uh, I mean, because there are four features, we're going to have maybe two features. Or we'll have a weight layer and a bias layer. Okay, actually, let's reformat our question. So we have a neural network, and all we want to do with the neural network is we want to a neural network that takes in, okay, four values and gives out two values as a prediction. Think of it like that. Okay. We just want to make a neural network that takes in four values and gives out two values as a prediction. Okay. And let's actually start. Whoops. Let's start it off over here. Okay. So now I'm going to put over here import torch first. Then I will put torch dot, and you can actually create a seed. Okay. So torch manual seed 42. This means it will deterministically generate this whenever I do torch.random. That's all it does. Okay. And also, just to explain, torch random outputs, the range of outputs for torch.random is a distribution or a mean around zero with a standard deviation of around one, right? So they are typically between -3 and +3, right? That's basically what it is. That's what torch.random gives us. So if I do torch.random of three different values, I will always get the same output. Okay. So I can say is equal to that. Torch is said, my bad. See. Okay. Oh, oops, I was supposed to print X. So if you see this will always give me the same value no matter what because it's deterministic. Okay. So we are trying to use a very deterministic value when you're doing it. And what we'll do is, let's say our input features are actually 4, and we have what do you call 3 batches. That means there are 3 different samples. Okay, so think of it like modeling a sequence. Think of it like modeling a very specific sequence of numbers, right? So, for example, you had a sequence of numbers like let's actually generate those numbers right now. So yeah, for example, you had 3 sequences of numbers. These 3 sequences. Okay, so I can just actually copy this and then do over here x of these bunch of numbers. Okay, now the question being the big question being that these sequence of numbers that exist will map out to some y. Okay, it'll map out to some two-dimensional y. So maybe you want to map this to this somehow. That's basically what we're trying to do. Actually, you know what? Maybe we are trying to predict something. So maybe it's just a one-dimensional thing. Okay. And maybe this is what you want the output to be. Okay. So this is like some expected randomized output. Okay. And if you were to look at this in this neural network, the weight should be like one for this, it should be 000 for each, because we have just copied the first value over here, if you observe it, right? So you have a sequence of inputs and you have a sequence of outputs. Okay. And what you're trying to do is you're trying to create a neural network. So you want to model this, right? So usually for a neural network, y is equal to w into x plus b. Okay, or rather x at w plus b is the correct way to put it. X at w plus b. Okay, and then the actual output after a nonlinearity would be to add a nonlinearity. But because it's a single layer function, we can actually skip the nonlinearity if you'd like to. Okay, but mm, I think we should still activate it. We should still put an activation function. So we should say a is equal to torch dot ReLU of y. Okay, it could be something like that, and we could also put w is equal to torch dot random of not 4 comma 2. Okay, it will be the output is going to be a number which will be basically a 1. Okay, because we wanted to predict only one output because there's only one column. So there's like shape rotation type of shit that we are doing. So we got x, w, and b. Okay, and now the x at w, a is equal to torch.relu this. And now what we should also do is we should probably also put requires grad is equal to true. Yeah, and now we will be able to go backward after the activation function. So we can write over here, print y, print a. Okay. So we got a sequence, we got a tensor. Okay, we are first going to print x. So print, so x is deterministic. We are printing what is w, which is 4 comma 1. We printed what is the bias, and then we we did the calculation, and we then printed y. So this is the predicted output, 1.46 minus 2.47. But ideally, this should be the output. Why this should be the output? Y true. Y ground truth. It's like a very dumb letter, but just stick with me on this. Okay. So loss. So think of it like a target, or rather than ground truth, you can call it as yeah, ground truth slash target, anything. Okay. And what we need to do is we need to compute the loss. So we can just take the mean square error loss for something like this. Say loss is equal to this activation, this tensor that we have is equal to, where is that? Where is that? Where is that? Um, it's basically the mean of all of these values, right? It's the mean of all of those. So it is basically loss of A minus the ground truth, Y ground truth, right? Whole square, right? This whole thing mean, because it's a tensor, right? So this would be the loss. So if you were to compute the loss in this case, wait, and I have loss, and then you would do actually loss that backward, right? Wait, so over here. Okay. So now if you look at it, we are getting some very specific values. We got, this is 1 second, and just to increase the readability, I think I should have done this before. Okay. Cool. This is better. So XWB we have, and now we have Y, and now we have output after activation, which is A, right? So A minus loss. So then loss, computed loss, right? Now what we're going to do is, this should make it much more readable. So XWB, now the Y value is this. Output after the activation is, this is what we got after output. This is the loss, which is 1.3. Our objective is to turn the loss negative as much as possible. So now when we do x dot grad, we can see this value, right? And when we do w dot grad, okay, actually, let's actually just print out. This is the way in which the values of x need to change for us to get our target. W dot grad is this, and B grad is this. Okay. So what we need to do is, we actually don't even care about x dot grad per se. We care more about w dot grad. Okay. Oh, wait, what is none? Interesting. Oh wait, I think I made a small error. This is capital W. This is capital W. I think I should use the same case. I think I should have just put W for all the variables and made it all small, right? Like this W. And now that way it won't um, get bugged. Okay. is still none. Hmm. I think I made a small bug somewhere. Mm-mm-mm. Did we do loss dot backward? Yes. Loss is equal to a minus ground truth the whole square. Um, hmm. And loss dot backward is what we did. So he says that it is none. Give me a moment. Give me a slight moment. Oops. So I actually completely forgot. It was a very simple, stupid bug. If you've seen, I had completely forgot to enable the gradient. So this is what I had forgotten to do, and this is what I should have done. Okay. So now we know this is XWB. This is the ground truth. We want to match this sequence of numbers to go through this neural network and give us an output like this. This is ideally how it should give. The Y value is this, and the output after activation is this, and then the loss is 1.3006. W dot grad is a tensor of these values, okay, and B dot grad is 1.53. That means we must reduce the value of W and B for us to do it, right? So how do we do that? Now all we can do is very, very simple. We can just say with, so ideally what we do is we need to now create a learning rate. We actually create a loop, okay, and we have to iterate it a couple of times to get the actual value, right? So that we can keep updating the value of W until it becomes the actual, until W turns into something good, right? Because currently W is this value, is this. So we have to keep updating it, okay? So a very simple way to do this would be to write LR is equal to R 0.0, okay? Now W is equal to W plus, sorry, W is equal to W minus W dot grad, okay, star LR, oops, star LR, and the same, right? So now this is the updated W and B. Now that W and B have been updated, I can again calculate the loss, okay? I can again do this. So I'm gonna just copy paste this segment, okay, and paste it over here. And now you will see, so I'm gonna just mark this with XX, yeah. And now you will see very clearly over here, the loss is 1.2629. Here the loss is 1.3. Here the loss is 1.2629. So this actually flows like a, it flows completely like a loop. So it's a small training loop that we have actually established over here because I've done it multiple times. So simpler way to do this would be to put this all into a loop. Like basically update W grad, and then we would then set W grad to 0 again. So now we would say W grad set back to 0 now, right? And what we would do is we would basically run this maybe 100 times, okay? We would basically capture the loss, do the same calculation again and again until we get the answer. So this is the initialization. So after initialization, so print, we have finished initialization. We will now run a training loop, basically. Okay. And for this training loop, for I in the range of 1,000, maybe we would say, let's start with something like 20. Okay. So for I in the range of 20, all we do is we do this. We just calculate Y, we calculate A, We calculate the loss. After that, we do loss dot backward. We find the gradients of W and B. We know the learning rate. So we update our weights and our biases, print W, print B. And then we set the gradients back to 0. And we run the same process again and again and again, right? That's basically what we do. And just so that we can make this a bit better, I'm just going to comment out the print statements. Otherwise, we're going to have way too many prints. Okay. We're going to remove the output activation and this Y as well. We are only going to keep printing the loss. Okay. Loss. And we're going to say loss at ith iteration is this loss. That's all we're going to say. Did you get it? So you will see the loss coming down. And then as that keeps happening, then after 20 iterations, you can print W and print B. So this will give us updated value of W and B for it to work. Okay. Oh, wait. A non-type object has no attribute 0. I think we forgot to... Okay, wait. Let's actually see what's happening. Finished initialization. Loss at the 0th iteration is this. The grad attribute tensor is not a leaf tensor. Won't... Okay, wait. I think this is another very simple bug. Let's actually test this. Okay, just a quick update, a primer. So basically, there was a very small error. I had to basically do torch.nograd and also the input tensor shape. So you can't manually set W is equal to tensor of 0 because right now the shape of W grad is a matrix of 4 different elements, right? If I were to print W grad, we'll get 4 different elements. Actually, you know what? Let's actually print and I'll explain to you what the error was. So let's say we are only doing it 2 times. Okay. We are iterating it only 2 times as we have seen over here. And now what we're trying to do is we are going to try and we have to do no grad. This was the first error. So ideally I was tracking it and this was causing bugs. So I can do the same thing, but it has to be under the banner, like here. The same as this. So I can just do this. This is the same as what I've written above. There's no difference. So you see this value of 19th iteration is 0.8066. If you were to do it, okay, I think we have 0. None type object has an attribution of 0. Okay, yeah, I think there is definitely a small bug over here. Maybe I'm discovering the bug. Oh, okay. Okay, I think the bug is right here. Look at that. W minus is equal to, okay. So now if I were to do this, oh, interesting. Set W, none type object has no attribute 0, but why is it none? Okay, I'm actually curious. Okay, explain this error. Um, okay, well, this just sucks. that didn't explain it, but basically, give me a sec. Give me a sec, actually. Okay, guys, I actually figured out what the error was. So basically, what happens is this is called an in-place operation. Okay, this is an in-place operation. I actually asked ChatGPT. So this will substitute the grad in place. But when I do it like this creates a new tensor. A new tensor. So ideally, because it creates a new tensor, it causes a bug, right? And ideally, what we would do is we would have to just again convert this into a tensor. So you would do over something like this. I hope this would work then. If it creates a new tensor, then it should probably be something like this is equal to, right? And same for this. Let's see if that works. If this um, workaround will work, right? Okay, no, I think there is it still goes to zero for some reason. Hmm. I mean, is it even possible to do this? It's a very weird paradigm. Like it'll work with this. That's because it's an in-place operation, right? Let's actually test it out a bit more. Okay, so I actually reasoned through why it was not working. This is actually not possible. We can't actually do this. Why we can't do this is ChatGPT has given a brilliant answer already. That's because it does graph detachment. So it's the same as saying um, you're creating a new tensor, right? This is creating completely new tensor. This has no connection to the previous computation graph, and it becomes a fresh leaf tensor. The dot grad from the old W is lost. Therefore, future backward passes will compute gradients with respect to the new tensor. And a new tensor doesn't have any gradient, which is zero. And that is precisely why it throws this error, because it's none. The new gradient is zero, right? So it's detached from the graph. And there is quite literally no other way to do this than doing this. There is literally no other way. Otherwise, it's like assigning a new thing. So I guess we will have to stick to standard practices and we can't make our own. So I'm going to actually delete these lines because they're a bit problematic, and we're going to continue by doing this. Okay, we're going to continue doing this, and now this should be fine, as you can clearly see, right? So now this whole gradient descent is actually working, and we're actually training our neural network in a way. So if we were to do this to 200, then you would basically get it at a 200 iteration. The loss is much lesser, right? And let's say we were to do it at 1,000 iterations, right? Then the loss is, well, I think I did it as 100. Just make it 1,000. There we go. Okay, so we can see it has actually stagnated. Did you see that? You see something very specific is happening. It's not improving as fast anymore. It was stuck 2.31, 2.30. That means it's moving really slowly. So as time goes on, you want to reduce your learning rate, basically, right? So if you say if I greater than 500, then LR. So you by default you can put LR is equal to 0.01, else it's equal to 0.005, right? Something like that. And you can do different conditions. So you can do maybe above 200, or I don't know, like, yeah, I think above 500. This is like a good bet. Let's see what happens. So you can see it's coming to 0.4242, and without without having this, 4227, 424. Okay, so this is a bit worse, but basically, it should actually help it. Wait, maybe we should just increase the learning rate. What if we were to put it as 0.02? Now what happens? 4206 is what it's stuck at. Huh. What if we were to basically make it? Hmm. So basically, there are different ways to optimize it. So there are different optimizers that are used to optimize it, and that's when we use Optim. But this is just one of the ways of changing the learning rate and then negating it with the gradients to do it, to actually do it, to modify it, right? We could also do, like, we could just maybe only change B, and that could also give us an answer. So we can change different levers to get different answers. But all in all, I'm just saying that the final B and W is this. So then print Y, right? Sorry, print the function, right? print this whole thing. Do the forward pass. So let's do a final forward pass, right? This, oops. So now this value will be pretty close. And you know what? Let me actually remove the prints because there are way too many prints. We're gonna put if I percentage 100 0, then only print this. Oops, not this. I think that should be good. So now at every iteration, so you can see the loss where as it has come down at the 0, it was 1.3, then it being 0.43, and it is slowly going down from 0.42. Okay, with a learning rate of 0.02. And if we take two large steps, that will be very bad as well. Like, I mean, not very bad, it depends. I think this, it's just stopped at, because I think bunch of dead neurons over here. I think if we were to print the grad at that moment, then we would see what's actually going on at that moment in time. So I can just do this, that, still, right? And you can see the gradients are zero. That means they're not changing, they're dead. There are solutions to this, if you can clearly see. By the 100th iteration only, it's dead. That's because our step is so large. 0.01. Let's see. Okay, no, by the 100th, it is still, the gradient is still zero. That means there is no update, right? So it's useless to go even above 100. So this actually shows us that it's not doing it perfectly even at 100, that that the neuron is dying really, really quickly. And that's probably why you will do torch.nn dot functional dot leaky leaky. Let's see. That I think this is not the only solution, but just one of those solutions. But you can see we seriously got a lower value. We are getting to a lower loss number with uh, uh, with leaky ReLU, clearly, because it's probably stepping in the right direction, and also our learning rate is lower, so that also helps. But we can clearly see that the gradients are zero. That means they're dying out, and that is bad. So, how would we actually fix this? Let's actually think a bit for ourselves. So to maybe diagnose this better, let's actually take a smaller look. Let's go to 100 iterations itself, and let's keep printing at every 10th iteration instead, right? I percentage 10 is equal to 0. I think that's the best way, so we can identify what's going on. Okay, we are seeing it goes down in the 10th itself. Okay, I think we are breaking something. So let's just go to 10 iterations, and let's go with this. Okay, let's give that a moment. Okay, guys, honest mistakes. I was just thinking, and I think it's just me being stupid. Because if you were to see that we are setting the gradients to 0, it's obviously going to show us a 0 over here because we haven't even done backward yet. That's why, right? So ideally, this whole segment would only be here. Does that make sense? So this part is not supposed to be here. It's supposed to be after we calculate our loss, like here. So now this is what will give us the right value. I apologize for being such a bad teacher in that way. So we can go back to 1000. Yeah, so now the gradients are flowing. We are sure the gradients are flowing. And yeah, leaky ReLU does help because it does help us get to a lower loss value, which is 0.3979, right? It sort of does help us get to the lower loss value. So this was basically the whole thing, right? This was the neural network, and the final output 0. This thing y value output after activation 0.471400 0.3974. Is this close to this to the expected ground truth? It should be 0.33, -1, and 0.46. So if you see this, this is very close to 0.46. The first value is 0.33, which is also sort of close to 0.41, and the middle value is 0. So it is sort of getting close to that value. It is sort of getting close to that value, right? So dot nn dot functional leak. Yeah, so we are getting we are getting closer to the value. Basically, we're getting closer to the final value. This is just a very simple example, a very stupid example, but I think this sort of helped me sort out a few issues when I was doing forward and backward pass. We were basically just trying to match this sequence of numbers with this sequence. So sorry if this was a bit confusing, but this was also a bit of learning for me, and how we made a very simple neural network to match a set of numbers input to a set of numbers output. Okay, I hope you liked this, and if you didn't, you can just comment. But yeah, that's about it. Thank you.